Hey there, everyone. It's October. That's the spooky month. Put on some face paint or wear a costume. Just, go bananas. Of course, when it comes to scares, no zombie, alien, or even vampire can compare with the fear of math. But don't be a scaredy cat. We have technology to help us with our next unit. Particular equations. When looking at graphing and transformations, we saw that functions had a few different forms, namely the parent form with no transformations, and the general form with all of the transformations included. If you actually replace all of the placeholder variables in the general form with specific number values, you get what is called a particular form of the function, or a particular equation. Since there's like infinite-ish numbers that can go into general forms of functions, there are infinite particular equations that you can create. While understanding how functions operate in a general sense is important to grasp the nature of graphing, particular equations are needed to solve for specific data points, or to create functions that model a real-world situation as accurately as possible. So, how can we use all those equations that we graphed in the previous unit to find solutions to various types of algebraic problems? Well, grab a spooky seat and your favorite haunted pillow or blanket, and a nice glass of the blood of the innocents. And let's dive in. Boom. Solving a particular equation can be done by taking certain algebraic actions to rearrange the equation so that a variable is by itself on one side of the equal sign. These algebraic actions are typically called opposite operations and are used to undo or unravel certain parts of the equation. If the equation only has a single type of variable such as x, the solution will end up being a numerical value. If there are two or more different variables in an equation, you can't get a number for any of these variables necessarily without substituting in a number for one of the others, but you could still solve for a variable technically by getting it isolated on one side of the equation and moving everything else to the other side. When it comes to finding numerical solutions to equations, the opposite operations you need will change depending on the type of equation you're looking at, and can be incredibly difficult, if not sometimes impossible, to solve and calculate just by hand. So what are we gonna do? I mean, by this point, you probably already know what we're going to do, right? Can you guess it? Come on, think about it. Yeah? Do you know? It's Desmos. We're gonna use Desmos. When typing a particular equation into Desmos, you can find a solution to the equation by tracing the graph until you find a coordinate with a y value that matches the other side of the equation you were given. If you don't feel like scrolling around with the trace function though, you can make a second equation with y being equal to whatever the other side of the equation was, and find the intersection of the two resulting graphs. When two graphs intersect, it means that putting in the x value of the intersection into both equations yields the same answer, which will be the y value of the coordinate of intersection. Since one of your equations is simply the solution to the problem, the lines will intersect at the x value that produces the desired y value, or gives you the answer, so to speak. This could technically be found on a table as well, but the issue with this strategy is that you can't input y values into a table, only x values. This would mean you would just need to pick x values to try until you found the matching y value, and that could take a really long time. Or it might not even be possible. The intersect solving method will eliminate the infinite possibilities and narrow things down to just answers. Another way you could solve certain equations is by subtracting everything away from one side of the equation, leaving just a zero behind. This will make the solution, x values, the coordinates where y equals 0. These coordinates are called X-Intercepts. Certain equations will have multiple X-intercepts, meaning their equations may have more than one solution. Sometimes both answers count as correct and must both be listed as solutions. Other times you may find that despite having more than one solution, one or more of them may not make sense in the context of an application problem. Take a look at this graph here, a negative quadratic equation. By looking at the X-intercepts, we can see that this equation has two solutions, x equals -1 and x equals 3. These are both fine as is, but let's say that we were told this parabola is modeling the motion of an object launched into the air from 3 feet off of the ground, with the time spent in the air listed on the x-axis. In this case, the solution at x equals -1 no longer makes sense because it's talking about negative time, or time before the ball was thrown. This is impractical for a number of reasons, so we simply reject that answer and go with x equals 3 in the context of this situation. These methods are incredibly convenient for solving equations and can change the whole game up in terms of learning complicated solving methods. An example of this is finding an equation from a graph. Here we have the graph of an exponential function that we want to find the explicit equation for. We know the basic structure of the equation, a times n to the x, but without any details on the axis, it's difficult to see exactly what we're looking at. The only clue we have to go off of here are the two coordinates on the line that they give us, 1, 4, and 3, 1. These coordinates imply that whatever our equation is, if we plug in 1 for x, we'll get an output of 4, and if we put in 3 for x, we will get 1 as an answer as well. Since both of these points are on the same line, it would stand to reason that both of these equations represent the same line, meaning their missing a and n values must be the same. Since the variables in these two equations are the same, this means that we have created a system of equations. Systems have some unique properties, including the ability to use one equation as an operation for the other. If we divide the left and right sides of the top equation by the left and right sides of the bottom, we find that the a values cancel out, and the powers on n will subtract since they have the same base. This leaves us with 1 over 4 on the left and n to the power 2 on the right. We can now solve for n by square rooting both sides of the equation, leaving us with n equals 1/2. We can put this value back into either equation and calculate everything out with one of our coordinates to solve for a, which is equal to 8. We can take the coordinates out of the equation now, replacing them back with x and y, and then filling in a and n with the values we found, giving us the particular equation of the graph we're looking at. While we found the solution, we again had to take complicated algebraic operations to achieve our result. What if we had a formula that could shortcut this process for us? Let's go back into this problem, but instead, just turn the 2 points listed into x1, y1, and x2, y2. Just 2 different points on the same line. That means our 2 equations initially will look like this. Let's perform the same operations on this system as we did to the previous one. The result, which we see after doing these operations, is these 2 formulas that are now generalized to help us find a and n. If we put this into Desmos, we can save it as a way to find exponential equations given any 2 points on the line. It may not surprise you that there are formulas for other types of functions as well, all of which can be found using the same method of solving a generalized system. Here are the formulas for a linear equation, and here are the formulas for a power function. We could even sort of use these methods to solve for a logarithmic function with a base that's not 10. These methods aren't necessarily viable for some of the other functions, and become even trickier when transformations are introduced into the equations. For these types of functions, we can use a powerful technology trick called regression to find the particular equation. Let's say that we have the following graph. We can tell that we're looking at a square root or some sort of radical equation, but we're not sure about transformations or other numbers that may fully create this particular equation. We were given 3 different points on the line though, so let's go ahead and put those coordinates into a table. Notice that when you create a new table that the x and y at the top both have subscripts, x1 and y1. These are important for the regression, so leave them there. After typing in the table values, let's go to the next line and write out the general form of a radical function with a few changes. 1. We're not going to include the b-value transformation this time. More on that later. 2. Type a 1 after each x and y. This will create subscripts on each of the variables each time you type them, giving you x1 and y1. 3. Use a tilde, which can be typed by holding shift and then pressing the key to the left of 1 at the top of the keyboard, instead of an equal sign for the equation. This will generate a set of values for a, h, and k, allowing you to fill those in and find the particular equation for the graph. You can do this with just about any type of equation, but the results lose accuracy if you input too few coordinates. Even with a substantial amount of coordinates, I found that it's actually incredibly difficult to get the regression to register b values correctly. I'm not entirely sure why, but my theory for this is that most b values can be moved out from under the special operator sometimes, which drastically changes their value, even though the overall equation stays the same. This gets even weirder when it's paired with an already existing multiplier, like an a value on the outside of the equation. For these reasons, we're just going to leave horizontal dilation or b values out of our problems where we try to form a particular equation from a graph or table. Cool. So we can solve equations using Desmos, and we can find equations using Desmos, and we can graph and transform all the equations that we saw using Desmos. So, at that point, we could do everything.
Hey, Jack.
What's up?
What about trig and polynomials?
What about trig and polynomials? You may have noticed that we didn't solve any trig equations or really look at any polynomial equations yet. Trigonometry is a broad enough subject that we're going to be giving it its own unit, the next one, in case you're curious. But polynomials are something that we should definitely cover here, especially since we didn't talk about them too much or graph them really in the last unit. So what's up? Polynomials are single variable equations with one or more terms linked through addition and subtraction. In order for there to be multiple terms and a single variable, the variables must each have different powers, keeping each term separate. Polynomials not only tend to have multiple solutions, but have the ability to be broken down into a product of linear equations, a process we call factoring. You've most likely factored a quadratic at this stage in your math career, and you may remember some or even all of the many rules and strategies one must employ to properly factor a quadratic. You may also remember factoring polynomials with third or even fourth powers in them. This is usually done through some form of polynomial or synthetic polynomial division, another complex process that can be incredibly messy and doesn't always work by hand. Luckily, just like everything else, we can use Desmos to factor a lot of these equations using only a little bit of extra math. Let's say that we have the following cubic polynomial, 6x cubed minus 37x squared plus 32x plus 15. If we put this into Desmos, we find three intercepts that serve as solutions to the equation. X equals negative 0.3 repeating, which we can think of as negative 1/3. X equals 1.5, which we can think of as 3/2 or 3/2. And x equals 5. If we put these into parentheses, we get the following three linear factors, making sure to reverse their signs so that they're properly written. X plus 1/3, x minus 3/2, and x minus 5. We're doing good so far, but we have two issues presently. One, it would be nice if the fractions in the factors were integers instead of fractions. And two, the 6 attached to x cubed doesn't show up if we multiply these factors back together. In fact, none of the coefficients seem quite right here. We can actually deal with both of these problems at the same time by distributing numbers to the parenthesis sets that have fractions in them, so they can be eliminated. In this case, the first parenthesis gets a 3 distributed to it, while the middle one gets multiplied by 2. Not only will this get rid of the fractions by canceling their denominators, but you may have noticed that the two numbers that we distributed multiply to 6. This will make a 6 show up in the equation if we were to multiply everything back together and expand it out to its original polynomial form. Ooh, okay, I think that's everything. It was a lot, I know. And there's still more waiting for us on the other side. Math never ends. Prepare to be sucked into an endless void of equations and numbers and patterns and tables and graphs and solutions and systems and matrices and vectors and coordinates and derivatives and integrals.
You killed Hero with the math.
He literally stopped functioning.